Good day from Chem Help ASAP. Let's see now what happens when we flip a cyclohexane that has substituents. So we have two flippings of cyclohexane on the screen. And so I'm going to make modifications to these. But at this moment, they're complete molecules. But let's change that. Let's say we don't have hydrogens everywhere. Let's change one of these hydrogens, and I'll change the hydrogen on carbon 4. Let's change this to a simple methyl group. Whoops, and I messed that up already. That's going to be this one. Okay, so here's a methyl group. We would say that this methyl is equatorial. We'd also say it has an up orientation. The bond is pointing up away from the atom it's bonded to, carbon 4. And so when we flip the ring, this methyl group will still have the up orientation, but it will be axial. So here's now carbon 4, that's axial. We're going up from the carbon to get to the methyl group, and so this is axial up. So we've drawn everything the same. Now, when everything was hydrogen, we said that these chairs had equal energy. As it turns out, when we have R groups, like a methyl, they are not equal in energy. When the group is axial, it actually starts to bump into the other groups that are axial in the ring. There's a little bit more space for this methyl group, or whatever the R group is, in the equatorial position. And this results in some strain. It's some steric strain. There's some steric repulsion when you put your R groups in the axial position. Therefore, this particular chair would be less stable. And this one would be more stable. So there would be a preference in this equilibrium. The left-hand side will be favored. In general, you want equatorial groups to be, you want your R groups to be equatorial if you can. Now, let's make another change here. Let's go to the bottom. Let's put 2 R groups. Go crazy. 2 R groups. We'll keep our methyl the same. And now, let's change one of our other atoms. And the atom I'm going to change, I'm going to go over to carbon 2, and I'm going to change this to a chlorine. And let's change this as well. This will become a chlorine. So this chlorine is axial down. And when we flip the chair, it's still going to be down, but it's equatorial down. Now, if we were looking at this molecule and look at the different flips and say, which conformation is better? We wouldn't like this one on the right because we say, uh-oh, that methyl group is axial up and it's going to bump into the other axial groups. But then again, we'd say the structure on the left has the chlorine. And the chlorine is axial, and that chlorine group is going to bump into the other axial groups, these hydrogens. So which is worse? Well, as it turns out, people measure the energy it costs to put different R groups, whether it's chlorine or carbon or something else, into the axial position. And these are called A values. You can look these up on Wikipedia, and there's no reason to memorize these values. But it turns out methyl is bigger than chlorine. So, as it turns out, the cost of putting our methyl group in the axial position is greater than the cost of putting the chlorine group. Therefore, this would be less stable. This would be more stable, and our equilibrium would reflect that. I can't talk in, right? This would be more stable, and our equilibrium would reflect that. We would tend to favor the left-hand structure. So this is how we talk about substituted cyclohexanes. It gets a little messier, but we need to be cognizant that when we flip the chair, groups, when they go from axial to equatorial, when they go to axial, they're in a position that can create some steric repulsion, and we have to be mindful of that.